So let me start without much ado. Yeah, so this is a joint work with Azizul Haq, which is in progress. All right. So what is it? Let me start my screen. So hope you can see that. So this is on class groups, n rank of class groups. All right, at least two. That is the title of my talk. So what's an ideal class group? We have seen enough definitions, but let me again begin for students. So take a number field K and let OK be the ring of integers, and collect all the non-zero fractional and integrand ideals of OK, call it I of K. And within that, look at the subgroup of principal ideals. Okay, call that as P of K. Now P of K, so I of K is a abelian group, and P of K forms a normal subgroup of I of K. Therefore, the factor group I of K by P of K, it's an abelian group. It is called the ideal class group of K. All right, and is denoted by H of K. And it's well known that H of K is always finite, follows from Minkowski's work. And the order of H of K is called the class number of K. And usually it is denoted by H of K, small h of K. All right. So one of the problems is to classify number fields which are class number 1. All right. So in this case, for imaginary quadratic fields, the problem is completely settled. We have only 9 fields, namely for corresponding Q root minus D, corresponding to D is equal to 1, 2, 3, 7, 11, 19, 43, 67, and 163, which have class number 1, and none of the others have class number 1. All right. However, for and for real quadratic fields, we know many of them which have class number 1. For example, for Q root D, corresponding to D is equal to 2, 3, 5, 6, 7, 11, 13, 14, and all. All right. But we don't know all of them. And still the conjecture of Gauss that there are infinitely many real quadratic fields with class number 1 is open. All right. And a related problem is, as again based on conjectures of Gauss. So one knows that there are infinitely many real and imaginary quadratic fields, each divisible by a given integer n. So this is one of the classification again of fields whose class number is divisible by a given integer. A lot of work has been done in this, and we have seen in Professor Renate's talk also. So Nagel has studied for imaginary quadratic fields the divisibility of class number by imaginary by n. Yamamoto and Weinberger for real quadratic fields. Kalyan Chakravarti and Ramurthy, they have studied for real quadratic fields with class number divisible by 3. Kalyan Chakravarti, Azizul Haq, Kishi, and Prem Prakash Pandey for divisibility of class numbers of imaginary quads under some conditions. U for real quadratic fields under some conditions. And also, there is a lot of work which deals with parameterizing these quadratic fields by certain numbers. All right, D's. Okay, so that's a well-studied problem. And one of the problems that is of interest for us today is the n rank of class groups of number fields. All right. So what is n rank? What do we mean by n rank of a class group? So let n be bigger than 1, be an integer, and G be a finite abelian group. By n rank of G, we mean the largest positive integer R, such that G contains Z by nz to the power R as a subgroup. So n rank of G is R here. All right. And if G has an element of order n, then obviously the n rank is at least 1. All right. And as we have seen in the first talk of yesterday, a more precise statement was there. So this is Cohen and Lenstra prediction. A positive proportion of quadratic fields whose class group have n rank at least 2. They predict that. All right. So in this direction, Yamamoto proved the existence of infinitely many imaginary quadratic fields whose class groups have n rank at least 2 for odd n. All right, existence. Okay, and U, he parametrized, gave a parametric family of imaginary quadratic fields whose class group has n rank at least 2 for some odd integers n. All right, which is bigger than or equal to 3. All right, and for higher rank class groups, Craig proved the existence of infinitely many imaginary quadratic fields with class groups having 3 rank at least 4. And Lorenthe and Quiver gave 3 imaginary quadratic fields with class groups having 3 rank 6. Kishi and Komatsu, they gave a parametric family of imaginary quadratic fields with class groups having 3 rank at least 3. Sorry. So, but however, a parametric family of imaginary quadratic fields whose class groups having n rank at least 2 for arbitrary n doesn't seem to be known to the best of our knowledge. And for real quadratic fields, it is known only for when n is equal to 3, 5, 7 due to Craig and Mestre. All right. Therefore, it is a good problem to see, can we parameterize this family of quadratic fields whose n rank is at least 2? And we have made an attempt, and the work is still in progress, as I say. All right. So what is the main result? The main result is take any positive integers, take a, b, c, and n be positive integers. This is a standard, method that we have adapted. So construct this number d, which is 2 times a to the power n plus b to the power n times c to the power n minus, take this expression, that is an plus an minus 1b plus an minus 2b square and so on up to bn, and square it, minus a minus b square times c to the power 2n. All right. You will see in the proof why we have taken this kind of number. So let d be any number of this type. So our main theorem is, so with d as defined above, okay, and a is not equal to b, okay, suppose d is positive and square free, and assume that d is at least 4 times abc square to the power l, where l is the largest prime divisor of n. Okay. Then the theorem is the class group of q root minus d has n rank at least 2. This is the main theorem. All right. So some remarks. We can choose ABC such that d is square free and positive. There are a few numbers that we have already computed. And if n is itself is prime, then this can be reduced. The assumption that d is bigger than 4 abc square to the power l can be reduced to d bigger than 4 times abc square, and therefore it will allow more members in the family. On the other hand, if a is equal to b, but a is not 1, b is not 1, then d is not square free. All right, from this equation number 1, and our proof doesn't work. Okay, so in this case, we think it is not easy to show that n rank is at least 2, even if it exists. All right. On the other hand, when a and b are 1, then we, as a corollary, we get that this quadratic field Q square root of n square minus 4c to the power n, the n rank of the class group of this is at least 1, provided 4 to the power cn minus n square is bigger than c to the power n and is square free. So this follows from the theorem by taking x is equal to n and y is equal to c in the proof. All right. So this is the main theorem. And I would like to outline the proof of the theorem, which is very simple and standard. So we need to show that the class group of Q root minus D contains a subgroup which is isomorphic to Z by NZ cross Z by NZ. I hope you are able to hear me, no? Because I'm not able to see myself. Right. And
yes.
Yeah. Okay. Thank you. So with the construction of D that we have defined before, which is this one, let us take x1 to be ai minus 1, bi minus 1 plus summation of that plus a minus b, c to the power n. All right. And y1 is equal to ac. All right. Then you see that when you do x1 square, this is square of the first expression minus 4 times y1 square, which is 4 times a square c square. Then by the definition of D, you will get this equation number 2. Okay, x1 square minus 4y1 to the power n is equal to minus D. All right. This is simple elementary calculation. All right. Okay. Similarly, put x2 is equal to an minus 1, this expression an minus I times b I minus 1, I is equal to 1 to n, and then plus b minus a times c to the power n, and y2 is equal to bc. All right. Now, again, if you square this x2 and then minus 4 times y2 to the power n, you will see that that is equal to minus d. All right. So the equation 2 and 3, please remember this. Therefore, from these equations, the 2 can be written as, by taking minus d to the left hand side, one can write it as product of x1 plus square root of minus d by 2, x1 minus square root of minus d by 2 is equal to y1 to the power n. We have divided the 4 on the right hand side we have brought it to the left hand side. And this tells us, okay, now observe that the ideals, in the ideal level, these numbers, x1 square plus square root of minus d by 2, x2 to, square root of d by 2, these are co-prime. All right. Because you see x1 and x2, x1 and y1, they belong to the ideal generated by these two numbers, x1 plus square root of minus d by 2 and x1 minus square root of d by 2. All right. And GCD of x1, y1 is equal to 1 because of equation 2. All right. Therefore, that means 1 belongs to the ideal generated by x1 plus square root of minus d by 2, x1 minus square root of minus d by 2. And since 1 belongs to the ideal generated by these two, therefore, the ideal generated by these two will be the entire thing, entire ring of ring of integers, which is not true. Therefore, each of this idea, they are co-prime, right? And therefore, since the product is a power of y1 to the power n, therefore each of them must be power of some ideals. So let x1, the ideal x1 plus square root of minus d by 2 is a to the power n, and x1 minus square root of minus d by 2 is a bar to the power n. Okay, for some ideals a and a bar. A bar is the conjugate of a. All right. Now similarly, the second equation, the equation 3, can be again split in the same way. So we will get ideals b and b bar such that x2 plus square root of minus d by 2 is equal to b to the power n, and x2 minus square root of minus d by 2 is b bar to the power n for some ideals b and b bar. B bar the conjugate of b. All right. Okay. Now let us denote CLA with ideal class in Q root minus d containing A, and CLB with ideal class in Q root minus d containing the ideal B. All right. So we will show that the classes CLA and CLB generate a subgroup in the class group of Q root minus d, which is isomorphic to Z modulo nz cross Z minus nz. Okay? And that will prove our theorem. Okay, because then that will show that the n rank of Q root minus d, class group of Q root minus d, is at least 2. All right. In order to show that the ideal class A containing A and ideal class containing B generate a subgroup, okay, we need to show that the order of class group of the ideal class A containing A, CLA, and CLB is n, and they are distinct. All right. And to show this, it is enough to show that the ideal A to the power P, B to the power P, or A to the power P, P to the power Q, now A to the power P or B to the power Q, or A to the power P times B to the power Q, and this A to the power P, B bar to the power Q is not principal for any divisor, prime divisors of n. P and Q. Take any prime divisors P and Q of n, show that these ideals are not principal. That will show that the order of CLA is n and order of CLB is 1, and we will prove our theorem. That proves our theorem. Okay. Again, it's easy to show that AP is A to the power P is not principal for any prime divisor P of n. All right. For that, suppose, as the standard method is, suppose this is principal. Okay. So A to the power P is U plus V square root of minus D by 2 for some integers, rational integers with same parity. Okay. Suppose it happens, we will arrive at a contradiction. Okay. Now, this means that A to the power n is nothing but U plus V square root of minus D by 2 to the power n by P. Now, A to the power n was already x plus square root of minus D by 2. All right. And comparing the imaginary part, it implies that V divides 1, that is V is non-zero. That is the crucial point. V is not equal to 0. And therefore, taking norms on both sides, the norm of A to the power n is nothing but y1 to the power n because of the previous equation. A to the power n, A to the power n bar was equal to y1 to the power n. Okay. Taking norm both sides, we get y1 to the power n is equal to u square plus dv square by 4 to the power n by p. And this is at least u square plus d by 4 because v is not 0 and v square we are taking to the power n by p. And by our assumption on d, because d is at least ab squares, abc square to the power l, where l is the largest prime divisor of n. So this is bigger than ABC square to the power ln by p. And you can forget about few numbers here. So this is bigger than AC to the power ln by p. Okay, which is, but AC is nothing but y1. So this is equal to y1 to the power ln divided by p. But L is the largest prime divisor of p. Therefore, y1, this gives us that y1 is bigger than y1 to the power L by p. That is not. Okay? Therefore, A to the power p is not principal. All right, simple proof. And in a similar way, we show that this B to the power p is also not principal for any prime divisor Q of n. Okay. Now, the funny part, the important thing is to show A to the power p, B to the power q is not principal for any prime divisor p and q of n. All right. So this is done in the following way. Okay. Suppose A to the power p, B to the power q is equal to principal, which is u plus v square root of minus d by 2 for some rational integers with the same parity. Then again, looking at A to the power pn, B to the power qn, which is equal to x1 square root of minus d to the by 2 to the power p, x2 square root of minus d by 2 to the power q, because A to the power n is x1 plus square root of minus d by 2. All right. And then simplifying it, you will get that this is equal to 1 by 2 pq, 2 to the power pq times this expression, a double sum of ARS plus BRS square root of minus d. This is again a simple calculation, because whenever the powers are even, we get a square root of, we get a d, which is ARS. And whenever they are odd, we get a minus square root of d. All right. So this is simple. To show that A to the power p, B to the power q is not principal for any prime divisor p and q of n, suppose, I have done it already. What happened? Yeah. Now taking norm, we get y1 to the power pq, y2 to the power qn, y1 to the power pn and y2 to the power qn is equal to, taking norm, u square plus v square d by 4 to the power n, which is at least u square plus d by 4 to the power n. Okay. Now again, since d is at least 4 times abc square to the power l, this implies y1 to the power p, y2 to the power q is bigger than abc square to the power l, which is equal to y1 to the power l, y2 to the power l, because y1 was ac and y2 to the power bc, y2 was equal to bc. All right. So therefore, this shows that they cannot be principal. So none of these ideals are principal, and that establishes our claim. So this completes the proof of the theorem. All right. Now, so this is a simple proof, and similarly, for real quadratic fields, we have the theorem. So let us form this number delta, which is same d with minus sign. Okay. And the theorem is, let A, B, C be distinct positive numbers. For any positive number n congruent to 0 modulo 4, let D be as defined by 8. That is that. Okay. Assume that D is square free and it is at least 16 times ABC square to the power 2L, where L is the largest prime divisor of n. Okay. Then the class group of Q root delta has n rank at least 2. All right. So this is for all n which are divisible by 4. Okay. So again, the proof is very much similar. So the main points are we need to construct two ideals, A and B, such that A1 x1 plus square root of d by 2 is a to the power n, and x2 plus square root of d by 2 is equal to b to the power n. Okay, then we have to show that if you take any prime divisors of n, then these are not principal. Okay. Same thing, we adopt the same technique, and the first two cases follow by taking norms of that equation, which gives us y1 to the power pn is equal to u square minus dv square by 4 to the power n. And from here, and look at, so if you look at this u to the power, take the square of this and then n by 2, then u4 minus dv square times dv square minus 2u square by 16 whole to the power n by 2 is bigger than d by 16. And since d is bigger than 16, abc square whole to the power 2l, this will give us a contradiction. All right. And similarly, exactly in the similar manner, we show that this a to the power, the ideal a to the power p, b to the power q is not principal. A to the power p, b bar to the power q is not principal. So this hypothesis d is bigger than 16 abc square to the power 2l is crucial for us. All right. So this is so far this is what we have been able to do. Okay. Now there are a couple of members that are in this. There are a couple of fields that we get, but we would like to know whether we have infinitely many of them. For example, if you put a is equal to b is equal to 1 and c is equal to 3 and take n to be 5, then our d is 947, which is square free and all. Similarly, you can find plenty of examples. For example, a, b, c, d, a to be 5, b to be 1, c to be 3, d. Then we get our and n to be 5. Then we get our the d number d to be 35509, and so on and so forth. So there are plenty of examples, but we would like to know whether it contains infinitely or plenty of them. Right? Also, we would like to know, to get a lower bound of such fields, quantitative results. So let us say we restrict the discriminant to be up to x, then how many such fields are there? So this is the work in progress that that is going on. So this was the main thing that I wanted to report. The second thing, because I have some time, I wanted to say that in the I have attended all the previous sessions, conferences in this theme, and in last time's conference, I've reported a work in progress, and that we have done it successfully. And I would like to just mention that results of that. All right. I will take few more minutes. All right. So that was about the biquadratic fields. Okay. See, the class number 1 problem is important because once you have class number 1, then the ring of integers, they form PID. They become unique factorization domains. All right. Thing is, we know that if an integral domain is Euclidean, then it is a principal ideal domain. That means it has class number 1. However, the converse is not true. So even if you have the integral domain has class number 1, PID, but it is not necessary that it is Euclidean. That we have seen in the imaginary quadratic fields. We have 9 imaginary quadratic fields with class number 1. Only 5 of them are Euclidean. All right. So let's look at this number field K, which is Q square root of M square root of N, square free integers with at least one of this Mn negative. Such fields are called imaginary biquadratic fields. All right. Now, class number 1 imaginary biquadratic fields have been completely classified. So there are 47 of them. All right, which is listed below. And the problem is they have class number 1, whether they are Euclidean, which is, do they admit a Euclidean algorithm? So the ones with the pink colored one, it was known that they admit Euclidean algorithm. Okay, there is a Euclidean function defined in the ring of integers. Okay. However, it was not known for the other 34 imaginary biquadratic fields. So this was the work I reported last time, which was in progress. And look at other quartic fields, which is imaginary cyclic quartic fields. Recall that the conductor of an imaginary cyclic quartic field K is defined as the smallest positive integer F, such that K is contained in this cyclotonic field Q zeta F. All right. And Bennett says that he has classified all the imaginary cyclic quartic fields of class number 1. And she showed that they in fact correspond to fields have conductor 5, 13, 16, 29, 37, 53, and 61. So we know that they have class number 1, but it was not known whether they're Euclidean. They admit any Euclidean algorithm. Right? So this is the work that we have done, and with the Subramani was my student, former student. Now he's in IIIT, Chennai, and Usha K. Sangle, who is a faculty, who was a postdoc here and who is a faculty in SRTM University. So these are the results. So let's take K to be Q root M, Q square root of M, square root of N. So the theorem says that all imaginary biquadratic fields of class number 1 are Euclidean. And similarly, all imaginary cyclic quartic fields with class number 1 are Euclidean. So this has appeared in this Rendikonti journal this year. So the main thing, the interesting thing that we did not report in the last time because we were working on this. So the main point was to study, main thing depended on the structure of the ring of integers. All right. So if you look at the imaginary biquadratic fields, which are listed by Ks, K1, K2 up to K7, then their unit group, OK star, is isomorphic to C4 cross Z. Okay. And there are other fields which are listed with else. Their unit group is isomorphic to C2 cross Z. And the other rest of them where the unit group is isomorphic to C6 cross Z. So we were applying a result of our previous paper, which we did for real, showing Euclidean algorithm in real quadratic fields, and then in cyclic cubic fields, which were the topic of the first 2 conferences. So that theorem did not apply because the structure was different for certain quadratic fields, and then therefore we had to really work a little hard to ensure that the main result that we were applying is true. So I don't want to go into details of what was the thing. So the proof involved a result of Ramamurthy, which says that if you have a number field and if the rank of the number field is R and it admits the ring of integers admits a certain number of primes, let's say R primes of certain type, S primes of certain type. R is the rank and S is the number of primes of certain type. And if this R plus S is bigger than or equal to 3, then there is a Euclidean algorithm. Then the number field admits Euclidean algorithm. That means the ring of integers admits a Euclidean function. Okay. So that was the main result. Now for all these cyclic, this Galois quartic fields that I listed, the rank is 1. The unit rank is 1. Right? And therefore we needed to show 2 primes in the ring of integers, 2 primes of certain type, which were called admissible primes. Okay. Therefore, in each of the field, we needed to ensure that at least they admit 2 admissible primes. Okay. That we did by using SAYS. We gave an algorithm and made sure that each of these fields they admit 2 admissible primes, which are in the right corner of this table. Okay. And yeah, so this SAGE program gives us all these things, and this algorithm is available in our web page, and also it is copied in the link is copied in the paper. Okay. And it's the same thing we did for cyclic quartic fields. We looked at each of these conductors, looked at the corresponding field, and gave 2 primes, P1 and P2, in the ring of integers. These are of special type. These are admissible primes. And therefore, this proves that the Galois cyclic quartic fields are Euclidean whenever they have class number 1. Okay. So we have some more problems here. And as I said in the previous thing also, maybe in the next episode of Kalyan's conference, maybe we will have some more thing to report. So I think I will stop it here and wait for any possible questions. Thank you very much for your patience.
So Prem, are you there? Okay, so Srinivas, could you please reduce the volume of the output unit? Your phone also maybe.
Record